And I'm grateful to organizers inviting me in such a wonderful place. And today I will speak about special Ulrich bundles on surfaces, which will overview already known constructions of rank 2 Ulrich bundles on smooth projective surfaces. So I will start with the introduction, but the introduction is almost covered by Gunnar's talk in yesterday, so he isn't here. So I can save my time a lot. So for simplicity, I'll only think that the base field has characteristic 0 and H is always O1. And D is the degree of X, which is H to the N. And let F be a coherent sheaf on X. So yesterday Gunnar defined what is an Ulrich sheaf. And there are many different equivalent conditions, but today I will use the condition as cohomology vanishing. So for instance, hi to the f minus ih equals to 0. It means that f is 0 regular in the sense of Castellano-Mumford. And also we have a further vanishing. With respect to minus j plus 1h, for j is smaller than the dimension, it means that F dual tensor with canonical sheaf is n plus 1 regular. Okay. Then, as we discussed yesterday, this sheaf has a very simple cohomology tables, and I add some remarks. So F has the cohomology table of F is nothing but the constant multiple of the table from the structured sheaf of this projective space. And why we are calling this F as an Ulrich bundle? So if F is an ACM sheaf, which occurred in the yesterday talk by Professor He, so it means that now our space is smooth. So this is nothing but F has no intermediate cohomology. Then F is locally free. So in particular, Ulrich sheaves are always locally free over a smooth variety. And of course, there are many other equivalent conditions to define an Ulrich sheaf. But today I will mainly use F is Ulrich if and only if the following sheaves are acyclic. So acyclic means that all the cohomology vanishes for all I, and j goes from 1 to n. So because of this reason, many people who studies derived category of Fano varieties are interested in Ulrich sheaves because they are orthogonal to the line bundles. And final remark is also was in Gunnar's talks and also in Frank Olof's talk. So from an Ulrich sheaf, we considering its state resolutions and considering the cohomology table. So this plays for I. Let's say this is J and this is I. So since any Ulrich sheaf is zero regular, so the state resolutions can appear on the level of global sections, and since it has a same type as a coherent, structure sheaf of cohomologies, so except here, and all the intermediate cohomology vanishes, and from here, at the level of -1, it survives. So the entry Ij is given by the dimension of cohomology groups twisted by J minus I. So the total degree is a J. So the zero regular implies that the maps occurring in the state resolution from here are not very interesting. They are very simple and almost trivial. And by the same reason, this part is also not very interesting. So the only interesting part is coming from the -1 level to the zeroth level. And Gunnar explained yesterday that this map, precisely speaking, to pass through the U functor defined by Eisenbud and Schreier. So this map computes the Chow form of the original variety. In fact, the R's power of the Chow form, where R is a rank of this Ulrich sheaf. So a naive question. Now everybody considering this as an Eisenbud-Schreier conjecture.
I think question is different than conjecture. I put question when I think it's interesting, but I'm not making a prediction.
Well, in their paper they didn't mention that this is our conjecture. In fact, this question can be found on 1980s by many commutative algebraists, including Bernd Ulrich himself. But now everybody thinks this is a conjecture by Eisenbud and Schreier. So the question is simple. Does an Ulrich sheaf always exist? And if yes, so if there is, what is the minimal possible rank? So far the question is so difficult and we don't know for almost all cases. But for instance, if X is a curve, then the question is quite simple. So let's say only one example without details. So there are only one example. Is a twisted cubic. So we can find Ulrich sheaves on twisted cubic by this way. And then one can check that F is Ulrich, and this map between the Tate resolutions of level -1 and level 0 is now recognized as a linear map. On certain Grassmannian lines in P3. And this 3 by 3 matrix will compute the determinant of this linear map, computes the R of C, the Chow form of the twisted cubic. But unfortunately, the question is so difficult and we don't know the answer for even for smooth surfaces. So I will explain what is known for smooth surfaces. So a fact is that what we know is a hypersurface in P3 has an Ulrich bundle. But there are many, almost never given surfaces can carry a Ulrich line bundle, and in particular there is a surface which does not carry any Ulrich bundle of rank 1 and 2 and 3. So if the answer is even for yes for surfaces, the minimal possible rank will start from 4. But we are much interested in rank 2 cases because we have many applications for rank 2 vector bundles, and also there are many kind of technical merits. So in many cases, in many significant classes of surfaces, there are rank 2 Ulrich bundles, so we are very much interested in rank 2 vector bundles. So one very important application proven by Eisenberg and Schreier is the F, let F be rank 2 Ulrich bundle with the determinant line bundle is isomorphic to omega x twisted by n plus 1h. Here n is the dimension. So this condition plays very important. So we can see that on the Tate resolution, we will have a term. So the Betti number in here will be 2D, and here will be also 2D. So we will have a 2D by 2D linear matrix is in Placer coordinates. And in this case, F induces a skew symmetric linear morphism. And so this is a linear matrices and skew symmetric, so we are interested in what's the Pfaffian, and Pfaffian equals to exactly the Chow form of X. So it is interesting to ask whether a given variety carries a rank 2 Ulrich bundles with determinant is exactly of this form. So there is another motivation or evidences from numerical properties. So let F be a Ulrich of rank R. Then, as we mentioned before, F minus H to the F minus N times H they are cyclic, so they have no cohomology. So in particular, all the Euler characteristic vanishes. So we have a number of identities thanks to Riemann-Roch theorem, and one can show quite easily that this F must satisfy the following identity. So in most cases, if we are interested R equals rank equals to 2, so that if determinant of F equals to omega x, twist by m plus 1 h, this satisfies the condition. So this is also the natural condition with respect to numerical conditions. So also we are interested now, from now on, we are interested in projective smooth surfaces. And F is called a special Ulrich. If and only if F is a Ulrich of rank 2, and the determinant is isomorphic to omega to the 3h. So a natural question is that which surfaces really carries a special Ulrich bundle? So over smooth surfaces, there is a very nice tool. The theorem is also proven by Eisenberg and Schreier. So every special Ulrich bundle on a surface F is so-called Lazo-Spelmukai. In other words, this means that there is a irreducible curve in the linear system defined by omega as 3, and also there is a line bundle on C which defines a G1K on C, and this K is the degree of line bundle equals to the 5 over 2h squared times 3 over 2h times k squared plus 2 chi of OS. And this fits into the following exact sequence. And here, the last map is nothing but the evaluation map, and A is now considering as a torsion sheaf on S. So such kind of bundles are called Lazarsfeld-Mukai, and this Lazarsfeld-Mukai bundle is a key ingredient for studying Petri map, and so it is the main ingredient for Brunet's theory of curves. And also, it can be, this kind of sequence can be used to classify prime Fanos ripples, as Mukai did in 1989. So Lazarsfeld-Mukai bundles are much easier to approach. So as a corollary, we can prove that every del Peso surfaces has a special weak bundle. Okay, let's try to figure out what happens. Let's see be a curve in omega 3H class, which is nothing but the minus 2 times Ks. So we choose C as a general. Then C will be smooth irreducible curve, lies on del Peso surface S. And the genus equals to K squared plus 1. And from the basic fact from Brunet's theory, of course there is a line bundle, but a general line bundle of degree equals to K squared plus 2, which is a genus plus 1 on C, is a base point free complete pencil. So this really fits into the above sequence, and one can check that the corresponding Lazarsfeld-Mukai is indeed Ulrich. And of course, from the construction, it must be special. So now at least we know one examples of surfaces which carries a special Ulrich bundle. And the next case, indeed the Lazarsfeld-Mukai bundles were studied. Originally it was studied over K-straight surfaces just to study what's the canonical syzygy of algebraic curves. So the next example was found on K-straight surface, is very natural. It was done by 3 people, Aprodu and Gavi Farkas and Ortega. And I think I forgot to say, but the condition of being Ulrich is very, very subtle to the choice of the polarization H. So it really depends on which embedding we choose. So H should be fixed. So this is a polarized K3 of degree equals to 2s. Unfortunately, their theorem does not show that the existence of special Ulrich bundles for all K3 surfaces, but if an irreducible curve C in 3H, because there's no Ks, has a base point free complete G1 5s plus 4, you can check that 5s plus 4 fits into this numerical conditions. Then S carries a special Uli. The proof is quite long, so I would like to tell you about only the main idea. So if S carries a special Ulrich bundle, then it must be Lazarsfeld-Mukai. So we study the space of Lazarsfeld-Mukai bundles of given rank and given C1 and C2. And if it is non-empty, if there is a non-trivial Lazarsfeld-Mukai bundle, then it can be realized as a, now it's not a moduli space as a scheme, but it can be realized as a moduli stack of dimension equals to 2s plus 10. But anyway, we can handle it as a geometric object and now we use a Serre's construction. So it means a Serre's correspondence between the rank 2 vector bundles and a section between the zero cycles on surfaces. And such a zero cycle must satisfy Cayley-Bacher equations. So we can find a parametrization not for the Uli locus, but for the failure locus to be Uli inside the space of Lazarsfeld-Mukai bundles. This is the candidate space, and now we are going to find a parametrization for the failure locus. And one can observe that indeed the failure locus is a proper closed subset. Indeed, it is closed because it's cut out by algebraic relations, and it is proper since one can check that the dimension is strictly smaller. So the conclusion is that a general object in space of Lazarsfeld-Mukai, so it is a general Lazarsfeld-Mukai bundle, is a stable special Uli. So that's the flow chart of their proof. The computing dimensions coming from a parameter. So we made a very huge space with constructed Grassmannian bundles over a linear system 3H, and considering the map between that Grassmannian bundles and relative real nether loss size and cut out by Grassmannian actions. So this will give a 2s plus 10. It can be checked as a 2s plus 10 for stable cases, but for unstable cases, we need to handle a little more technical issues.
You mean that taking the costing, having costing and consider unstable bundles?
Well, I'm sorry that I'm not an expert for moduli stacks, but if we
No, maybe I think moduli stack is just existence of the
Yes.
stabilizer, fixed stabilizer.
yes,
And coherent is much serious. The key point is that can you apply the deformation theory on that space?
maybe yes. And for unstable cases, we considering this state is hard. For instance, considering Harder-Narasimhan filtrations and computed all the dimensions of extensions and morphisms occurring into such kind of Lazarsfeld-Mukai bundles. And this is at most 2s plus 10. And for the stable one, it is exactly 2s plus 10.
The problem is that, and then if the moduli stack exists, then
Yes.
it's pure dimensional.
I'm not sure. I don't think so.
Maybe I think it's the very low cost is a cross of
So I omit the technical issues. So we choose a dominant component of Brillat loci, and considering the Grassmannian bundles over that component only, then the corresponding moduli is getting irreducible, and then we can do the same game for such kind of irreducible moduli. But in general, this is not irreducible. So we need to take a dominant irreducible component. Yes, thanks for the comment. So let's think a little bit more. So they need an extra condition so that curves in cubic sections have a base point free complete pencils, and such kind of Brillat type condition holds for the first a very general K3 surface outside of the union of Noether-Lefschetz loci. So that's why we need a very general assumption. But this condition is automatically holds for general cases, so that the K3 surfaces whose Picard group is generated by H. And this is a general case. And in this case, there is no odd rank Ulrich bundles, so rank 2 Ulrich bundles are the minimal. And another remark is that this method can be generalized to rational surfaces with sufficiently positive anti-canonical divisor, and also for Enriquez surfaces, which was worked by myself and also by Mariana Produ. But the proof is so complicated and we need extra assumptions, so I don't need to explain the details for these cases. But I'm going to overview a very, very simple argument suggested by Beauville. So in this case, he doesn't need such kind of extra Brillat conditions. So now S is a smooth projective surface with PG equals to Q equals to 0. And assume that H is so positive so that the linear system H minus Ks has an irreducible curve, then there is a special Ulrich bundle on S. And the proof is very simple. So in some sense, this theorem makes me frustrated because I did it in a very, very complicated way. And so let's take such an irreducible curve in this linear system. So the canonical sheaf is nothing but H restricted to C. And take A as a general line bundle of degree equals to the genus plus 1 as we constructed in del Pezzo surfaces, so that we can check that this is a non-special line bundles and also base point free complete pencil on C. And now we're considering the Mukai sequence coming from this pairs, then the dual of Lazarsfeld Mukai, and for simplicity I'll just note as a F sub C A. This is a dual Lazarsfeld Mukai. So we have an exact sequence. And now from the conditions that PG and Q both equals to 0, and also note that the last map is nothing but the evaluation of sections. So this evaluation map induces an isomorphism on its global section level. So we conclude that it's easy to see that the dual Lazarsfeld Mukai bundle has no cohomology on every level. And now we're considering what's the determinant of the dual Lazarsfeld Mukai. This is simple because it is supported on C, so it must has a OS minus C from the construction. So we use the identification it holds for every rank 2 vector bundles. So it is easy to compute that F twisted by plus H is isomorphic to F dual twisted by minus C plus H. And what is minus C? This is Ks minus H. So this is F dual twisted by K of S. So what happens? H2 minus A the Betti numbers are same by their duality. So all the cohomologies of F twisted by plus H is 0. So we have two acyclic bundles And if you are still remembering my definitions, then F twisted by 2H becomes Ulrich of rank equals to 2 and determinant equals to K plus 3H. So this is a special. So the proof is so simple that the first year graduate student can understand. And in particular, this kind of assumption holds for every Enrique surface without the Brillet type condition. And Enrique surfaces are quite interesting objects because there might so it has a chance to carry rank 2 Ulrich bundles, which is not special. So for instance, the construction starts from a general algebraic Kummer surface quotient by a fixed point free involution, then we get a Enrique surface and use the theory of so this Kummer surface has a very much elliptic vibrations, and such elliptic vibrations we can construct a Ulrich line bundle L on X, and we push forward, and then this is a non-special rank 2 Ulrich. And in most cases, this cannot be stable, and considering its Jordan-Helder filtration, the quotients must be a Ulrich line bundle. So it shows that there is an Enrique surface which carries an Ulrich line bundle. And I just mentioned without writing that very recently Borisov and Neuer conjectured that every Enrique surface indeed carries a Ulrich line bundle. And now we don't have enough time, so I'll just go a little bit faster. So Beauville shows that if S is a billion, then there is a rank 2 Ulrich, but it may not be it may not be special. So to save time, I'll just show the ideas. So this is simple. So E be a general Lazarsfeld-Mukai of rank equals to 2, C1 equals to 3H, and C2 equals to 5 over 2H squared. And I tried with this guy, the general Lazarsfeld-Mukai, but it is almost never be a Ulrich sheaf, but twisted by an element in dual a billion, then it becomes Ulrich. So all the examples I managed in this talk are the only known cases for Ulrich bundles on surfaces. And almost all of them are only works for minimal surfaces. So I would like to finish to introduce my small observations. So I was wondering, in the general cases, so we go back at general cases, smooth variety of dimension equals to n, and X itself is not a projective space. And let's F is a Ulrich bundles on X. So there are only two types of elementary management. So the first one, when we start from a projective variety, we can, considering its hyperplane section, it naturally embeds into Pn-1. Then one can easily check that F restricted to Hx is Ulrich. So in other words, this hyperplane cut makes a right way to produce a new Ulrich sheaves on hyperplane section. And the other elementary operations is given by linear projection at a point. So we choose P from outside of X so that this linear projection is becomes finite. Then it becomes an Ulrich sheaf on X bar. So in this manner, Ulrich bundles are well understood with elementary operations, but except for this assumption. So the only interesting cases happens when we take a projection center from the point inside of X. Then, now we have only a rational map. So I'll call it pi p, and for simplicity, considering this is embedded by a complete linear system. And how to recognize this rational map? So this can be done by considering blow up at a point, and then the map now becomes a morphism. So we have a map from X twiddle to Pn-1. Now it is defined by H twiddle defined by pullback of H minus E, where E is the exceptional divisor. So in this case, the inner projection, or we can say the blown up at a point, also carries an Ulrich bundle under a following natural assumption. So I need the assumption that H twiddle is still very ample, and we have a Ulrich bundles on X. Then there is a Ulrich bundle just constructed by the simple ways. And the proof is also very simple. So we push forward the structure sheaf of O X twiddle with this with blowing up. Then this is nothing but the structure sheaf on the downstairs. And also we can compute what's the analog for the multiple of exceptional divisor restricted to itself. This becomes also 0 for 1 to the n. So this is now the theorem becomes trivial. We just apply Leray spectral sequence. So we can compute the cohomology on upward from the downstairs. And this is 0 because of F is an Ulrich, so it satisfies the acyclic assumptions.
In the theorem, X is a suffix.
No, this is a dimension-free and also rank-free theorem. So F can be arbitrarily of arbitrary rank. X can be have an arbitrary dimension. Only what I need is X is smooth, and H twiddle is very ample.
And F is bundled.
Yes.
And your bundled F tilde is elementary modified bundle.
Right.
So why do you question smoothness in this equation?
Smoothness is always what I needed.
Well,
So without smoothness assumption, F twiddle is not a locally free. It's not a vector bundle, and I don't know how to control it as a geometric languages.
Maybe I think that X is locally free. So I think that you can prove this theorem by using local top. The language of vector bundle.
I think so. So
In the technique of the Professor Yeongrak.
I think you're right. So what I mainly use is nothing but this map. The condition just holds and the locally freeness. So maybe you're right. Thanks for the comment. So now I have less than 10 minutes. And we have a blow at a point. Of course, at a blowing up at multiple points. Sorry, not multiple points, but many points, which is not a fat point. Then, if we still have such kind of variampleness assumption, then we can have Ulrich bundles on blowing ups with by successive blow ups. So let's consider it in this way. So what we did is, if we have an Ulrich bundles lives on X, then we can take an elementary modifications and let's say just F twiddle. we can construct an Ulrich sheaf, Ulrich bundles on X twiddle, but how about the converse? So we know there is a Ulrich bundles on X twiddle. Can we construct or get any significant informations on Ulrich bundles on X? Unfortunately, the answer is no. So let's think about X is a Bernoulli surface in P5. Then the natural corresponding X twiddle is a cubic scroll. And for a cubic scroll is always linearly determinantal. So it is defined by 2x2 minors of this 2x3 matrix. For instance, we take a matrix as this form up to a certain coordinate change. Then we're considering this as a map between three modules, three sheaves on P4, and Igor Northcott complex of this phi will give the resolution of the ideal of X twiddle and now we take a phi 1, which is nothing but a phi twisted by degree 1. Then the Igor-Northcott type complex will give a, now it will give a linear resolution and this kind of linear resolution must indices is representing objects becomes Ulrich sheaf of rank 1, and since X twiddle is smooth, so this becomes an Ulrich line bundle. On the other hand, on the original surface X, there is no Ulrich line bundle on X. So Ulrich line bundle means that it means that to find a J such that H naught of OP2 J minus 2 and H2 of OP2 J minus 4 both vanishes, but there is no such J. And well, it carries a Ulrich sheaf, namely and this is special and this is isomorphic to the sheaf of tangent sheaf of P2. So my observation is that on going downstairs, we lose the information of Ulrich bundles in this manner. But if we are interested only in smooth surfaces and considering special Ulrich bundles, so we assume that still H twiddles is very ample, and we've only focused on special Ulrich. Then, as we've seen above, F twiddle is Ulrich, and it becomes special. And we begin with F twiddle, a special, Ulrich on X twiddle and H twiddle, then F constructed as a F twiddle twisted by E and pushed forward by sigma. Now it becomes locally free, and this becomes the special Ulrich. So it's almost the end of time, so I will only give a sketch, a proof. So from F is special, we have that the determinant is nothing but the pullback of omega x3h. Yeah, I will say it's special is a rank 2 Ulrich bundles with the determinant is omega s3. And we first showed that F, so the first statement is easy, so we are focusing on second statement. And from the F is Ulrich, and this is zero regular. So it is spanned, and we can check that this is also spanned. So using numerical conditions, one can compute the cohomologies on each fibers and conclude that the push forward of F twiddle twisted by E is really a vector bundle of rank 2. And now what we need to do is this rank 2 vector bundle is indeed really a special Ulrich. So first we need to check that this has a determinant equals to omega x3h. But this is clear because now sigma induces an isomorphism between these two sets, and the codimension 2 subsets does not affect on the computing determinant line bundle. So the determinant of F is omega x3h, since the upward, this is nothing but a pullback on by an isomorphism. And by Ulrich again, the cohomology on downstairs and the upstairs are equal. And we need one more vanishing twisted by minus 2h. In general cases, this has a technical problem, but only for special Ulrich, So for special Ulrich bundles, the vanishing of f minus 2h is nothing but an easy exercise using the Serre duality. A second.
Second equality.
Where?
How can you get the second equality?
Here?
Yeah.
This is nothing but f. F is a rank 2 vector bundle, so f is isomorphic to this.
Claim is that f is locally free.
We show that f is locally free.
You can show that f is locally free
Yes? Because so we can compute every fibers, including the exceptional divisors, and one can show that all the cohomologies are constant. So by Grauer's theorem, one can show that this has so the push forward of F triple E itself is a locally free of rank 2, and all the higher cohomology vanishes. So this is really an object considering as a vector bundle of rank 2.
Right. R is that right?
Yes, it's derived.
Not the direct push forward, just
Yes. So the direct push forward lies only at the zeroth level, and the corresponding object is locally free. So this shows that F satisfies acyclic conditions, which means that F is a special Ulrich. Okay, I think I've stopped here. Thanks for listening.